can see this is a minimization problem. All right, you want to minimize fx where you have three variables, x1, x2, x3. Okay, and b1 here is your base, right? This is your base. This is your start line. And your stopping criteria is when the start line less than 0.125. Okay, so what should we start with? You have to know how many variables? 3, right? We start with explore the step from your base 1, okay, which is 4 minus 2 and 3. All right, so we evaluate for x1, x2, x3, and the value of function. Okay. So the first evaluation, of course, start from the base point, 4 minus 2, 3, where the given function is 6, 7, 8. Okay, this is our starting value. All right. Now, in the second evaluation, so you move to what? Four minus 2, 3. So you move to the right to 4 minus 5 minus 2, 3. Okay, so your second evaluation is 5 minus 2, 3, which give you 6, 8, 3. All right, which is higher than the previous function from your base. So we decide that this is as failure. Okay. Then to the right fail, then again to the left. So you will have 3 minus 2, 3. All right. Then we have 3 minus 2, 3. You have 6, 7, 5. Then this is success. Okay. And then you move where? You move upside. Now the point becomes 3 minus 1, 3. Okay. So the next evaluation is 3 minus 1, 3. So we'll give you the value of 662. So there is another success. It is reduced from the 675. Okay. And then since this is success, no need to go down, right? And remember, this is 3 variables. So you need to consider the third variable. So from these 3, you should move where? To the front and to the back, right? This one is, okay. So to the front first, then the value, the point becomes 3 minus 1, 4. So check. The next evaluation is 3 minus 1, 4. It will become 1, 3, 3, 3, which is failure. Okay. So later you can check. You can do it by your own, one by one of this. Okay. So this is failure. And then again, we move to the back, which give you 3 minus 1, 2. The value becomes 293. So this is the most success. Okay. Between all evaluation. All right. Is that clear? This is fail. This is success. This is success. This is fail. This is success. Clear not? So now this is your new base. Okay. So you can say that your V2 now is 3 minus 1, 2. FB2 equals to 293. So from this base, you need to move patternly. So you have to make a pattern move. P1 equals to B1 plus 2, B2 minus B1, which give you 4 minus 2, 3, plus 2, 3 minus 1, 2, minus 4 minus 2, 3. Okay, so your P1 here is 201. And your FP1 equals to 106. All right. Any question? Clear? Then we proceed. We move from where? Our next exploration should be explorate from P1. Okay, FP1 equals to 106. All right. Anyone has question? And your next evaluation should be seven. Okay, so 201. So 201, move to the right, you will get 301. So next is 301. Your function is 107, okay, which is fail. Then we move to the left, which give you 101. Okay, then the value is 107. Still fail. Okay, and then we move upside. So we'll give you 211. 211, the function become 97, which is success. All right, no need to go down. Then move to the front. Okay, the point becomes 212. So when it is 212, the function is 272, which is failure. And again to the back, 210. Okay, so 210 will give you 32. So this is success. All right, then this is your new base. And find the new pattern move. And again, proceed up until, for this example, we should have until 55th evaluation. Okay, we evaluate until we reach H less than 0.125. But the idea here is how you move when the variable is 3. Okay, is that clear? Anyone has question? So usually up to exam practice, we have up until 3 variables. Otherwise, it is hard for you to do it manually. Okay, so actually it is just a consideration of move x-axis, right, left, move y-axis, up, down, and move z-axis into the front and back, just like that. Okay, you consider one by one the axis. Okay, so for this case, I hope you can try. If you have problem, you can ask until the last evaluation. We have evaluation 55. In this evaluation, all fail, but H is reduced. Okay, when can we reduce the value of H? Remember, when can we reduce the value of H? When there is all fail, right? When there is all failure, and also there is no change between the point, the base point is not changed, then you can also reduce the H step length here. Right? If B2 equals to B1, there is no function reduction. There is no function reduction mean it is failed. Then what we do is to reduce the step length. Right? And if your pattern move give the same value with the base point, then start the exploration again from your base point, just like we did in our previous example. All right, are we clear for this method? Anyone has question before we proceed with the next method? No question, all good. Okay, good. Okay, take your time to understand first. Evaluation 1. Evaluation 1, 6, 7, 8, 78. Which one? Which example? The new example here? 78? You got 78? Okay, let me check. X. Oh, no, no 6 here, right? Okay, thank you, thank you. This is 5. Saya pun. This one is 53. So 78. This one is fail. This one is success. This one is success. This one is fail. This one is success. So this is your new base, right? Okay, you can check. Okay, you can check. Then B2. This one should be 53. FP1. FP1 is what? FP1 is 34. Semua salah. Okay, so since the result of your fx here is same, then there is nothing changed with the base point here. Okay, so you can proceed. All right, clear. Sorry for the mistake. But the idea here is you need to know how it moves. Okay, wrong move means wrong point selection, means wrong value of function. Okay, so be careful with the points that you choose. All right, so that is how hook and Jeeves move to the solution point to find the optimum value by using what? By using this pattern search. Okay, this pattern search. Alright, so this is another direct search method where it moves in terms of pattern. Okay, in Fibonacci and golden search, it moves within the interval. Okay, and then for quadratic and cubic, it interpolate between the within the function evaluation of quadratic and also cubic. Okay, and now this is the movement process from pattern where we call it as a hook and Jeeves method. Okay, so any question before we proceed? So what should you know in this method is how can it start, okay, by using the exploration, and then the movement of the point, and then how to choose failure and success of the function, and then finding your pattern point, PI, okay, and then you should stop where? You should stop at when H less than the value given. Okay, we take B2 in evaluation 5. Evaluation 5. Where is evaluation 5? This one? So now no problem. All right. Okay, so I have attached in the e-learning notes from error. Tak boleh buka e-learning. Notes for steepest descent and also Newton's method. Have you opening? Okay, steepest descent and Newton's and quasi-Newton. So let's hope that we can finish up to at least Newton's method before the Hari Raya holiday. And also your midterm, right? Okay, let's proceed with Newton's and steepest descent. So in the previous semesters, we also have another direct search method, which is called Nelder and Mix method, but it is now omitted. So no need to discuss that. There is no mention of Nelder and Mix in your CI also. The Nelder and Mix, this is just for your information. The Nelder and Mix move in terms of triangle. As you can see in this optimization, the method is about the movement process, okay, from the starting point up until the solution point. So however it moves depends on what kind of method. Okay, so now for the next method here, Right, can you see the screen? Okay, so in this method, where we call it as a steepest descent method, the most classical method in gradient method. So as you can see, this steepest descent method is a gradient method where the movement process involve the gradient. Okay, just like before, it just moved directly from a point, from initial point to the next point, x1, x2, x3, okay, up to how many iterations in order to reach our solution point. Okay, so now for this steepest descent, we use gradient, okay, to move. We use gradient to move. So how can it move? That I will explain. So it use gradient. Okay, this method will use your gradient and function values, which is gradient is what? Derivative of fx. The direction of steepest descent is opposite to the gradient of the function. So the gradient, if the gradient is like this, and the direction is opposite. Okay, so that we will have the zigzag movement. All right. Therefore, the negative value of the gradient vector, this is the negative value of the gradient vector, is used as direct search to minimize the objective function. Okay, still we minimize the problem. Okay, why maximization we don't discuss in the class? Because we just can change the function value, then minimize the negative fx so that we can maximize the fx. Okay, so now the negative value of the gradient, which is negative del fx here, is used as the direct search. Okay, just before this we search directly, but now this direct search use the negative gradient to move. All right, move to where? To the solution point. So the derivative is orthogonal to the contour f at the point x. So this one, it is orthogonal because we use the negative derivative. Now, let fx be an objective function. So this is your objective function. You want to minimize this fx. If x0 is an initial estimation, then the point x1 is obtained through linear search along the direction d0, where d0 is your direction. Why? Because direction is gradient, right? So D is actually direction. But for this case, the direction is the negative gradient, negative del fx. And if for that certain iteration we start at x0, then negative del fx0. So in the next iteration, it moved to negative del fx1, negative del fx2, and so on. So the point x1 is obtained by the following. So this is how we move in the next iteration. X1 equals to x0 plus lambda naught d0. So what is lambda naught? Okay, so lambda naught here is just a constant chosen to minimize, where we need to find the lambda value first. Okay, so now this is the iterative method. This is the iterative formula of x1 equals to x0 plus lambda naught d0. Okay, you know that d0 is your search, is your direction search, negative gradient. Okay, at the point x0, and lambda naught is a scalar, right? It's a constant which determines the distance along negative del fx0 from x1. Okay, so if this is the point, this is the line of negative fx0, and then this is x0, so the length, the distance between this is given by the lambda. Okay, thus by using the information here, your x1 equals to x naught minus lambda naught delta f x naught, right? Okay, where lambda is a scalar. So in the steepest descent, lambda is chosen so that fx1 is minimized. So we need to choose that lambda in order to minimize the objective function. So our general iteration is given, okay, xi plus 1 xi minus lambda I delta fxi, where lambda I is chosen so that the function is minimized. Okay, let's take a look after this. There are several ways to find lambda. So we need to find the lambda. Okay, where we minimize the function with respect to lambda, that is the derivative of the function with respect to lambda equals to 0. Then we need to solve the equation. Then the value of lambda will give lambda I. So we have our objective function, right? In order to find lambda, so you need to differentiate that f with respect to lambda and then equal it to 0. And then we need to solve this equation in order to find the lambda. So this is one way to find the value of lambda. Okay, or we can use interpolation, quadratic and cubic method to find, minimize fx plus lambda d when the search from xi in the direction of di. So usually we use the first method here, which is easier. Okay, so the direction search are orthogonal to each other, right? The direction search are orthogonal to each other. That is del fx1, let's say 1, times del fx naught equals to 0. So how it moves? Okay, how it moves. So let's say this is the contour of f. Right? And this is your starting point. Okay, remember? Let's say this is your, okay, let's use quadratic. This is your quadratic line. This is the most minimum point. This is, but the movement is moved within the contour here. Okay, so how it moves? It moves orthogonal to the contour at point x. Okay, so this is your x naught, right? So it moves in the negative direction, negative fx naught. Okay, to this is your x1, and this is negative direction of fx1. Okay, as you can see, this is orthogonal to each other. And then move to x1 to x2. Again, move to x3. So here is negative direction of fx2. Again, it is orthogonal until you reach the solution point. So the movement process is always orthogonal to each other. So we call it as a zigzag phenomenon. Is that clear? So it is always move orthogonally until you reach the solution point. So why it is always orthogonal? Because we move negative that gradient. Okay, is that clear? Any question? So this is the explanation. We start at x0. Okay. We start at x0, evaluate the derivative of fx0 and move in this region until f stops decreasing and start increasing. This happens at the point x1 where del fx0 is parallel to the contour through the point x1. So until it reach to x1, now it is parallel, then again you apply the gradient. Repeat the process. This algorithm is good for a circular contour. Okay. So what are the steps? Okay, let's take a look at the steps together with the example. Okay, let's choose example here. Okay, the third one. All right, can you see the screen? Okay, so now this is the algorithm. Okay, let's do this algorithm together with the example here. Right, let x not be a minimum estimation. So now we have a problem to minimize the function of x1 minus 2 squared plus x2 plus 1 squared. Okay, we start at 1 minus 1 over 2. So now, as you can see, we have two variables. So let x not be a minimum estimation. So x not, okay, solution. We start with x naught equals to 1 minus 0.5, right? And we stop when epsilon equals to 0. Okay, usually epsilon is given, or the process stop at which iteration. Okay, usually it is mentioned, so no worries. Okay, now what is our first step? Okay, start with I equals to 0, right? So this is I equals to 0, right? Then calculate gradient. So before we calculate gradient, let's identify here. Okay, for x naught, 1 minus 0.5, f naught should be, just substitute, 1.25. Okay, and then we need to calculate the gradient g. So gx equals to derivative of fx, which give you 2x1 minus 2 and 2x2 plus 1. Okay, differentiate this partially one by one, and then we can find our g naught, which is just substitute the function g here with your x naught will give you minus 2, 1. Okay, so we identify g at the point of x naught. So g naught at point x naught. Okay, now we want to calculate lambda, right? So remember, in our iteration, we always update with these iterative methods, which is xi, which is now here is s naught, then I is 0, then x1, x1 equals to x naught minus lambda naught g naught. So x1 x equals to x naught 1 minus 0.5 minus lambda naught times with g naught, and you have here 1 plus 2 lambda naught minus 0.5 minus lambda naught. Alright? Okay. Calculate lambda naught, lambda I, such that fxi minus lambda igi equals to minimum fxi minus lambda gi, which give you the derivative of this equals to 0, and the value of that lambda minimize the function. So means that you have to have your fxi minus lambda igi. So this is your xi minus lambda igi. Okay, so this is actually xi, I is not minus lambda naught g naught. Alright, now your fx naught lambda naught g naught, which is also fx1, equals to, just substitute here, this one, substitute to your function. Where is your function? Fx. This one, x1 minus 2 squared here. So x1 now is 1 plus 2 lambda naught minus 2 squared plus minus 0.5 minus lambda naught plus 1 squared. Okay, so we'll give you, simplify this, you will have 2 lambda naught minus 1 squared plus 0.5 minus lambda naught squared. So this is fx naught minus lambda naught g naught, right? So calculate lambda such that this function equals to minimize the function. How can minimize the function? By differentiate f here with respect to lambda and equal this to 0, which give you, right, which give you for 2 lambda naught minus 1 minus 2, 0.5 minus lambda naught equals to 0. So solving this will give you lambda naught equals to 0.5. Okay, then you can have your what? Then you have your lambda. You have your lambda, then you can find your x1. So now x1 equals to x naught minus lambda naught g naught. Right? So now here this is your x1, right? Just substitute again 1 plus, okay, no need. You use directly. From here, x naught is what? X naught is 1 minus 0.5. Lambda naught is 0.5. G naught is minus 2, 1. So this gives you x1, 2 minus 1. Then you can calculate your f1, which is 0. And g1, substitute x1 to gx here, will give you 0. Now, the magnitude of G1 is equals to 0, which is less than epsilon. So the minimum value is x1, x2, 2 minus 1 will give you fx equals to 0. Why we stop? Because we reach the stopping criteria at epsilon equals to 0. Okay, any question for this method? Okay, try to understand first. If you have question, you can ask. The movement process become faster and faster after we reach advanced method. All right. Just before this, we just find directly one by one within the interval. But now it moves in terms of pattern. It moves in terms of gradient. So it accelerates the movement process. Okay. And also this is quite a simple example. That's why we just found our optimum point, our solution point at only one iteration. Okay, any question? Understand or not? So far, okay. Right, so this is steepest descent method. All right, try the first example. Just take only 2 steps of steepest descent. No need to reach until optimal solution is reached. This one. So you can check the example here and compare. you have question, you can ask.